Welcome back! In this video, I'm going to start with a quick refresher about time series. This is a time series course, so this video is an obligatory stop. I have to introduce time series. In this video, I will refresh the concept of time series and provide some time series examples. Then I will talk about univariate time series. Following that, I will show some multivariate time series and the formats in which we can encounter them. And finally, I will make a recap on regular versus irregular time series, stationary and non-stationary time series, and a short intro into the different components of a time series. If you are familiar with these concepts already, or you have already taken any of our other forecasting courses, then feel free to skip ahead to the next video. With this said, let's get started. Time series are data points indexed in time order. Or in other words, time series data is a collection of observations obtained through repeated measurements over time. Some examples of time series are the price of stocks and shares, sales under revenue, income through donations, or energy demand and energy production, the quality of the air, for example, through particle concentration over time, temperature, ocean tides, and also some medical signals like electrocardiograms or encephalograms, among other things. Here we have some visual examples of time series data. Here we have an example of rainfall over the years. In this plot, we see the number of people, or in other words, the population growth, again over the years. This plot shows us the number of passengers in an airline, again over the years, and here we have the signal of an electrocardiogram. How does a time series look like when we have it on a data frame? A time series has values, which is what we are often interested in, and it also has a time index, either as an additional column or more commonly as the index of the pandas data frame or the pandas series. What we see here is a single or univariate time series. Examples of univariate time series are the mean hourly temperature in London, for example, or the hourly energy demand in Buenos Aires, or the weekly sales revenue in our family store. In most cases, we will have more than one time series. For example, if we are forecasting sales, we probably have the sales of various items in our store. And here we have a data frame representation of that scenario, where each column represents one of our products, and the values in those columns are the sales revenue for that product over time, and in this case, it means day after day. Here we have a visualization representing those time series. This is an illustration that I took from the SK forecast documentation. This table representation that we see here is what we call wide format, where we have one time series per column. Examples of multiple time series are, as we mentioned, the sales of multiple products or the sales in multiple cities, and also the energy consumption in multiple households or the temperature recorded in multiple districts. More often, we will work with time series in a long format. This table is an equivalent representation of the multiple time series from the previous slide. But now we have all the time series in one column, and we have the product ID in a separate column. This product ID, or item as I call it here, is the time series identifier. It's what allows us to identify or separate one time series from the other. The characteristic of this long format representation is that we will have one or more columns that allow us to identify each time series. In this case, that column is the product ID. And in the long format, the index that contains the timestamp that indicates when the data was collected does not contain unique values because the dates repeat themselves for every time series. Time series can be regular or irregular. In regular time series, we take observations at regular time intervals. For example, in weekly sales, we have sales revenue for each week. If we record hourly temperature, then we have a temperature record for each hour. These are the time series that are the easier to work with and that also feature in most books and courses. But time series can also be irregular. In this case, observations are not taken at regular intervals. For example, patient records. We will have information about the patient when the patient showed up to the clinic, for example. Time series can also be stationary or non-stationary. In stationary time series, the mean and the variance of the time series do not change in time. What this means is that if we pick different windows in time across the time series, the probability distribution remains the same. The typical example of a stationary time series is white noise, which you probably know is a random signal. Non-stationary time series are more common. In this time series, either the mean or the variance or both change over time. Sales is a classic example of a non-stationary time series with an increase over time if the business is doing well, of course. Further discussion about stationary and non-stationary time series is beyond the scope of this course, but I will leave at the end of this section a thread that Kishan found that is super insightful in case you want to know more about this. Finally, you probably heard of the components of a time series. Time series can have a trend, one or more seasonal components, a cyclical component, and then the error term. A trend is a long-term change in the mean of the time series. For example, an increase in sales over the years. We can see the trend of this time series in this panel here. Seasonality, on the other hand, are regular, repetitive fluctuations that occur across the time series, like, for example, an increase in sales over Christmas. Year on year, we always see the same pattern that over Christmas we have more sales. Another seasonal component we see, for example, in car traffic, with a peak of traffic at rush hour and a decrease of traffic overnight. Time series can have more than one seasonality. And taking again the example of car traffic is also higher over the weekdays than over the weekends. So here we have a second seasonal pattern. Cyclicity are irregular fluctuations, for example, a decrease in sales during depression or war, or something external that repeats itself every certain time, but not exactly the same time. Finally, everything else that we cannot decompose into these components is what are called the residuals or the error term. In other words, irregular fluctuations over time. And this goes without saying, but some time series may not have any of these components, or at least decomposing them into these components is not easy. Kishan goes into more details about the components of time series in our other course on feature engineering for forecasting, in case you're interested. But coming up to the end of the video, why does all of these characteristics about time series matter? Well, because based on the characteristics of the time series, we will choose one forecasting model over the other, and if we're using machine learning models for forecasting, we will need to craft features to capture these characteristics for these models to be effective. In this course, we will go over the main feature engineering strategies to craft features for forecasting with machine learning. These are the strategies that are most widely used. And if you want to create even more powerful features, then check out our other course on feature engineering for forecasting, where we show you how to create features to capture, in addition, trend, seasonality, cyclicity, and much more. So let's wrap up this video with a summary of what we discussed so far. We mentioned that time series are data points indexed in time order, and that they can be regular or irregular. They can be also stationary or, more commonly, non-stationary. and that time series can be decomposed into defined components like a trend, one or more seasonal pattern, potentially a cyclicity, and then the error term. So that will be all for this video. In the next one, let's talk about forecasting.